Hi everyone, I decided to make a video over the cannabis lecture as a way to help you prepare for our upcoming exam on Thursday. So in this video you will find that many of the slides that we went over in class will be briefly reviewed again. And then I'll also go over some of the slides that, there were a few slides that I didn't get to go over in lecture, and so through this audio lecture I'm going to briefly go over them as well. And any other slides that we went over in lecture that I don't cover in this video lecture, feel free to let me know if you'd like me to go over it again in class on Tuesday. And besides that, we'll really dedicate Tuesday's lecture to going over caffeine. Okay, so I'm not going to go over every slide, but some of the important slides I will go over again here. So let us fast forward to the phytocannabinoid slide. So all of this we went over in class. So make sure that you review them. And now here. So what do we have here? Phytocannabinoids. Okay, so of all the phytocannabinoids, as you see here, THC and CBD are the ones that are mentioned. Why? Because these are the two that have been identified as the major neuroactive components in cannabis. That doesn't mean that we don't have other phytocannabinoids in the cannabis plant. We do, but the ones besides THC and CBD are considered to be weakly or not psychoactive phytocannabinoids, right? However, doesn't mean that they are pointless or useless. No, they may have medicinal potential that as of now is untapped, right? So there's still much to be learned about the cannabis plant. We don't know what effect each of these other phytocannabinoids have, or how much each of them contributes to the psychological and behavioral outcomes of cannabis use, or even how these different phytocannabinoids interact with one another. Now, when it comes to understanding the pharmacology of THC and CBD, we know a lot more about THC's pharmacology, right? The mechanism of action. Why? Because THC has received the most research interest and attention due to its psychoactive, analgesic, and appetite-stimulating properties. So, of all of the phytocannabinoids in cannabis, THC is the one that's considered the key psychoactive ingredient of cannabis. On the other hand, THC's sister molecule, CBD, which the cannabis plant actually makes from almost identical enzymes, is non-psychoactive. It lacks the psychotropic properties that produce a high, like THC. Now, because of that, because CBD lacks psychoactivity, for the longest time, THC was pronounced as the active component of cannabis. And because of that, research focused mainly on THC and basically ignored CBD. Because of the belief that activity meant psychoactivity, which, as mentioned before, is shown by THC and not by CBD. Now, looking back, this is seen as an unfortunate event because there are a number of actions of CBD that have potential therapeutic benefits, and these therapeutic benefits were overlooked for many years. Right? So, as mentioned in your book and by our group presentation, we know that CBD has therapeutic potential. And among the disorders being considered for possible targets of CBD are seizures, right? Epilepsy, neurodegenerative disorders, anxiety disorders, substance use disorders, psychosis, among other conditions. CBD has anti-inflammatory, anti-anxiety, antipsychotic, and neuroprotective, as well as other effects. So part of the antipsychotic effects of it are derived from its ability, CBD's pharmacology, to decrease the psychotropic activity of THC. So CBD, in a way, counters the psychotropic, the psychoactive effect of THC, and thereby decreases its THC's psychotic potential. Now, the major point of this slide was to show just how recent cannabinoid pharmacology is, right? The story of cannabinoid pharmacology began not too long ago. It began in 1964. Our major discoveries regarding this system took place between the 1960s to 1990s, and there's still much that's left to be understood. So isolation of THC took place in 1964, and after that, there was the search for the actual receptors that THC work on. When the receptors were discovered, then we wanted to know what are the actual internally driven neurotransmitters that act on these receptors. And now a lot of focus is on essentially, how do these endocannabinoids participate in various different mental functions. So the discovery of the first cannabinoid receptor was in 1988, and then that set into motion the search for the receptor's natural ligands, right? The endocannabinoids. And the two important ones that we talked about were discovered not too long ago, in 1992 for anandamide and in 1995 for 2-AG. Okay, now let's keep going forward. Okay. All right, so when the cannabinoid receptors were identified, the next task was to see where in the nervous system they're expressed. It turns out that they are very widely distributed and expressed by many different brain areas that are listed for you in the upcoming slides. So we see CB1 receptors to be expressed in areas such as the basal ganglia, the cerebellum, the hippocampus, the cortex, among other regions. CB1 receptors are expressed by these various neuronal populations, and you can find them mainly in presynaptic structures, specifically nerve terminals, so axon terminals, and axon segments near the terminals. Now, this is why THC, the major psychoactive component of cannabis, has such a profound effect, such a widespread effect on behavior and mental function, right? Because CB1 receptors, which THC activates, are expressed by so many different areas that are serving so many different functions. So that's why locomotor activity, your coordination, your memory, your verbal ability, all of that become acutely affected when under the influence of THC. Okay, so CB1 receptors are mainly found in the central nervous system. With respect to CB2, you can also find CB2 receptors in the CNS, but to a much lower degree. For instance, you can find CB2 receptors expressed by glial cells and also by some neurons of the brain, but again, at a much lower level than CB1. With respect to CB2 receptors, our second cannabinoid receptor, which was discovered after CB1 receptor, they were initially found in the immune system and then later in other tissue, such as bone, adipose, and gastrointestinal tract. CB2 receptors are in the brain expressed by microglia, the brain's immune cells, especially when those cells have been activated by inflammatory or degenerative processes. Okay, so again, you find CB2 expressed by the body's immune system, peripherally, and then also by the brain's own immune cells, the microglia. Okay, so the details for the mechanism of action of CB1 and CB2 receptors were discussed in class. If you need me to go over it again in class, I will, but so I won't go through those details, but I will just go over the main point, one of the main points here, which is the following. Activating cannabinoid receptors, CB1 and CB2 receptors, both of which are metabotropic receptors, leads to an inhibitory effect. So for instance, if CB1 receptor sits on a particular neuron, activating CB1 leads to that cell becoming inhibited. Now, how the cell is inhibited depends on where you find the CB1 receptor, right? So the way it's inhibited depends on if CB1 receptor sits on the post or the presynaptic membrane. So inhibition can look like hyperpolarization, so that the cell is less likely to generate an action potential when you find CB1 receptors post-synaptically. So if you find CB1 receptors on the postsynaptic membrane, inhibition looks like hyperpolarization. And hyperpolarization is a way of inhibiting the cell because you're keeping it from, or you're making it less likely to generate an action potential. Or if CB1 receptors are found presynaptically, inhibition looks like or is manifested in the form of inhibiting neurotransmitter release. So, given that THC in the brain activates mainly CB1 receptors, THC, if you remember, is a partial agonist for CB1 receptors, which are mainly found presynaptically, for instance on axon terminals, then activating CB1 receptors by THC leads to inhibition of neurotransmitter release. So if you activate CB1 receptors that are sitting on GABAergic, GABA-releasing neurons, that means those GABAergic cells will not be releasing GABA as much as they were before. Or if you find CB1 receptors on glutamatergic cells, then release of glutamate by those cells will become inhibited, and so forth, right? So the three mechanisms here, opening potassium channels, inhibiting voltage-gated calcium channels, or inhibiting adenylyl cyclase and cyclic AMP formation, all of those are mechanisms by which inhibition is induced. So opening potassium channels would be one way that you can inhibit postsynaptic cells by activating these metabotropic receptors. Or inhibiting voltage-gated calcium channels would be a way of inhibiting cells presynaptically, right? Because if you inhibit voltage-gated calcium channels, then exocytosis, which is the release of neurotransmitters, will also become inhibited. Okay, so for this here, make sure to go over this slide to see where are the many different areas that CB1 receptors are mainly expressed, right? The reason the hippocampus, basal ganglia, and cerebellum are highlighted in blue is because CB1 receptors are most highly expressed in these three regions. And then to a lesser extent, they're expressed by the various other regions that are on this slide. There are, something that I may have not mentioned in class is that there are a few cannabinoid receptors in the medulla. And that explains why cannabinoids have little effect on breathing reflex and other vital functions. So because you don't see as many of these receptors in the medulla, the cells in the medulla that are serving all of these various vital functions have a less likelihood of becoming inhibited and affected. So we also find CB1 receptors in the peripheral nervous system. Their main function there is to promote energy conservation and modulation, of storage, and modulating the storage and utilization of energy reserves. Okay, so now let's keep moving forward. So let's go to CB2 and talk a little bit about that. There has been a lot of focus lately on CB2 receptors and their immunosuppressive effects. We find, as mentioned before, that CB2 receptors are found mainly in the immune system in the PNS, of course among other tissues that were previously mentioned, in addition to being expressed by the brain's immune cells, the microglia, especially when these cells have been activated by inflammatory or degenerative processes. Previous studies have shown us that in response to injury or disease, including stroke, Alzheimer's disease, Huntington's disease, Parkinson's disease, we find that CB2 receptor density becomes increased in the CNS. So this suggests that receptor activation may have some protective effect against the destruction of our cells, our neurons, by the immune system. So there's a lot of focus on these receptors, on CB2 receptors, for the development of drugs that may help slow the progression of neurodegenerative diseases. Okay, so our brain has cannabinoid receptors, which we've been talking about, CB1 and CB2. And they were not, put in our brain for THC, but for our brain's own neurotransmitters that activate these receptors. The two main endocannabinoids that have been found are anandamide, or AEA, and 2-AG. And as you can see in the next slide, chemical analysis has shown both of these endocannabinoids to be lipids. You can see their lipid structure in the next slide. Now, there are other endocannabinoid neurotransmitters as well, but they're significantly less active, and their functional relevance hasn't yet been clearly determined. So we may find out more about these other endocannabinoids as time goes on. Okay, so what else? These two endocannabinoids, anandamide and 2-AG, they're made and released on demand by the postsynaptic cell in response to too much activity in the postsynaptic cell. So they are released in response to depolarization of the postsynaptic cell. 2-AG is a full agonist at the two cannabinoid receptors. Anandamide, though, is a partial agonist with a slight preference for CB1 receptors. And we say that because we find that anandamide has lower efficacy at CB2 compared to CB1. 2-AG is also considered to be the more important endocannabinoid. It's present in the brain at much higher levels than anandamide. Doesn't mean that anandamide isn't important. It's just that 2-AG, we find it at a much higher level compared to anandamide, and so for that reason, it's considered to be the more important synaptic signaling molecule. Okay, so now let's keep going forward. Okay, so the previous slide I went over again in class on Thursday. This is a very important slide. I'm not going to go over it again right now, but if any of you have any questions about it and would like me to go over it again on Tuesday, just let me know. But some other main points to just wrap up this endocannabinoid signaling would be to remember that the most common signaling of the cannabinoid system here is what's called retrograde signaling, in which the endocannabinoids activate CB1 receptors on nearby nerve terminals. You can have also non-retrograde signaling mechanisms where the endocannabinoids are made by the postsynaptic cell and, for instance, activate postsynaptic receptors to lower excitability of the postsynaptic membrane. But the most common signaling is this retrograde mechanism where the endocannabinoid is made postsynaptically, but it activates a presynaptic receptor. Okay, so the signaling mechanism is this retrograde signaling mechanism is usually mediated by 2-AG, and because the CB1 receptor is found presynaptically, you can imagine that 2-AG that's made from the postsynaptic membrane travels to the presynaptic membrane to inhibit calcium-mediated neurotransmitter release from the terminal. So activating the CB1 receptors presynaptically is going to lead to the inhibition of those voltage-gated calcium channels that we need, right, to get a calcium influx that will then set exocytosis into motion. So when these voltage-gated calcium channels become inhibited, that presynaptic cell can still fire action potentials and depolarize the axon terminal, but now this depolarization no longer opens these voltage-gated calcium channels because they have become inhibited via CB1 receptor activation. Okay, so this is called retrograde signaling because it involves this signaling molecule, this neurotransmitter, carrying information in the opposite direction of what's considered normal, what's considered normal is pre to postsynaptic signaling, but now we're having what? Post to presynaptic signaling. Okay. Now, overwhelming evidence shows that endocannabinoids in general mainly are retrograde messengers at synapses in a number of various brain regions, such as the hippocampus, which we'll be talking about more shortly. Okay, let's go talk about some of the acute effects of cannabis. Okay, so what we find is that marijuana affects various different cognitive functions, right? It affects learning, it affects memory, among other cognitive processes. There are two different types of studies when it comes to figuring out the effect of cannabis. We have studies that focus on the acute effects of cannabis, of marijuana, and then we have studies that look at the chronic effect. So let me just lay out very briefly how these two different studies differ. In acute studies, marijuana or pure THC is administered to participants who typically have a history of previous cannabis use. Then these results are compared with those that are obtained from matched participants that are instead given placebo instead of the active drug. So this is how we can get to how cannabis acutely influences someone's mental functioning. Chronic studies compare regular, sometimes heavy cannabis users against non-users when neither group is given a drug prior to testing. We want to know here, what is the long-term effect of cannabis on cognition when it is not, presently in your system, when it's not acutely administered. So what are the findings? Among the different cognitive processes, memory impairment is the most consistent and pronounced finding in studies of acute cannabinoid exposure. We see verbal and visual memory impairments, and including working memory deficits. Besides that, we also find deficits in verbal learning, in attention, in inhibitory control, and psychomotor function, such as reaction time. These functions are also reliably associated with acute cannabinoid exposure. Now, the learning effects of the learning deficits that we see can, for instance, be explained by activating CB1 receptors in the hippocampus. As you know, hippocampus is an area that's essential for memory formation. So it would make sense why learning would be affected if our ability to encode information and form memories of that information become influenced or inhibited. Okay, and we also see these learning and memory impairments in animal studies as well. Now, what's interesting is that if you administer THC with CBD, so pre-treatment with CBD has been reported to protect against the THC-induced deficits in verbal learning and memory. So again, if you remember, CBD has these protective properties that you also see in cognitive tests as well. Okay, so there's some other factors that influence findings. So for instance, amount of prior marijuana use has shown to influence the results on some of the cognitive tests. So heavier prior use reduces the adverse effects of acute cannabinoid exposure, and this type of finding has led to the hypothesis that behavioral or cognitive tolerance develops in heavy marijuana smokers. So again, there's some tolerance that's being developed to the subjective and cognitive impairing effects of cannabis in marijuana users. But how much tolerance, the degree of this tolerance, is going to depend on a number of other factors. So what are these factors? The pattern of use, or the amount of prior use, how long someone has been using, and how they've been using it, right? Is it daily? Is it weekly? Other genetic factors might be involved. But overall, this type of tolerance that does develop involves desensitizing and down-regulating CB1 receptors. So think about how that would make sense. If CB1 receptors activation of them has an inhibitory effect, then these different brain regions become less inhibited. If the individual has less of these CB1 receptors to become activated, or if these CB1 receptors are less sensitive due to one's prior heavy chronic activation of these receptors. So, since CB1 receptors are becoming downregulated, you can also then take away from this, or you should already be able to see and know that the nervous system is then changing in response to the drug. Someone that smokes regularly, they're changing their nervous system. They're not just having a momentary effect. Downregulation of receptors means that the number of receptors have decreased. And we always see downregulation in receptors when there's chronic activation of these receptors. It's a compensatory response of the nervous system so that your nervous system can try to establish some balance. If my receptors are now becoming overly activated by these exogenous, by these outside of my body substances, my body's going to respond to this overstimulation of receptors by lessening these receptors so that it can create some sense of homeostasis or balance. Okay, so we don't just see the downregulation of CB1 receptors in humans, we see them in animal studies as well. So animals that are receiving THC injections daily for 3 weeks, for instance, show downregulation of CB1 receptors and also desensitizations of the remaining receptors. And what we also see is that this downregulation is not short-lived, it's long-lived. It takes weeks after the termination of this study, right? So that means after THC administrations have been terminated, it takes weeks for these receptors to upregulate, right? So it takes a while for the normal level of these receptors to occur. So, I'm just going to repeat this point again. From studies, from PET imaging studies in humans, we have shown a widespread decrease in brain's CB1 receptor in regular marijuana smokers. Later in the upcoming slides, we're going to look to see how withdrawal symptoms in cannabis-dependent individuals is actually related to the changes in overall CB1 receptor binding. Okay, the last acute effect would be psychomotor performance. So our psychomotor abilities are also affected by chronic cannabis use and also acute. What that would be relevant for is driving. So things like reaction time, ability to perform divided attention, right? To be able to switch attention from one thing to the next and engaging in critical tracking, all of that become affected. And these effects are even more pronounced when marijuana is combined with alcohol. In studies, in driving studies in the lab, we see that it increases the risk of being in a vehicle crash and in an accident. The risk is somewhere between low to medium in magnitude. Okay, so what do we have here? We have a lot of previous studies that are showing us a negative relationship between cannabis use and academic performance. We don't currently know whether smoking marijuana, whether it causes a negative effect on academic achievement, right? We don't know if there's a causal relationship. Is it that early cannabis use causes a lack of success in school? Is that what's explaining the negative association between cannabis use and school performance? Or is it that lack of success in one's academic career leads to an increased marijuana use? Or could there be some third variable, like your classmate mentioned, that explains this dynamic, this negative association? Okay. So one explanation or one line of reasoning, one hypothesis is that persistent cannabis use leads to cognitive effects that impair school performance. So students who use cannabis heavily over a long period of time perform poorly in school because of cognitive impairments. So from this perspective, THC that's used heavily for a long term has a neurotoxic effect. It's impairing your various brain regions, and it's impairing your cognitive abilities, which is why you see this negative association between cannabis use and lack of success in school. So, studies such as Myers' study that's listed on this slide support this. So this Myers study is a prospective study of cognitive functioning in about 1,000 people in New Zealand. Participants were recruited into the study at a very young age when they were about 3 years old, and then they were subjected to neuropsychological testing before the onset of cannabis use at about age 13, and then again at age 38. What this study found is that the amount of cannabis use and the appearance of symptoms of cannabis dependence were significantly associated with neuropsychological impairments, including a lower IQ at the age of 38. This neuropsychological impairment and the lower IQ was found even after the study controlled for other factors, such as the level of education. Now, this is among the first data that suggests there to be a potential causal relationship between long-term cannabis use and cognitive deficits. Now, alternative hypotheses also have to be considered. So what are, two major alternative hypotheses for this negative association between cannabis use and academic performance? Another hypothesis, an alternative hypothesis, is the social context hypothesis. So this has to do with the social context surrounding heavy cannabis use at a relatively early age. The idea here is that cannabis use early on could promote the rejection of mainstream social values, such as education achievement, in favor of a more unconventional lifestyle. So this would be all the beliefs, right, the norms, the social context surrounding cannabis, and how that may be what's contributing to the negative association previously mentioned. Now, lastly, there's another hypothesis, another explanation, which has to do with motivational changes as a possibility. So research here has found evidence for apathy, aimlessness, loss of achievement motivation, lack of long-range planning in chronic cannabis users. So it's possible that some cannabis users experience a loss of drive and achievement motivation because of their chronic heavy cannabis use. And this could be what explains the inverse relationship between cannabis use and educational performance. However, there's this position is challenged by various other studies as well. So for instance, one can argue that it's actually possible for these personality characteristics that have to do with motivation to be a cause rather than a consequence of adopting a marijuana-centered lifestyle. So it could be there could be these personality characteristics that negatively influence motivation, right? It could be these personality characteristics linked to low motivation that leads to one picking up cannabis use to begin with, rather than cannabis use leading to lowered motivation and therefore deficits in school performance. And we have some studies that support this counterpoint. So we have studies that show there to be a disengagement with school performance or dropping out of school to happen simultaneously or even before the onset of cannabis use, daily cannabis use. So as of now, evidence is insufficient to determine a potential direction of causality with respect to cannabis use, motivation, and educational achievement. Okay, so memory and cognitive functions are impaired shortly after smoking marijuana. These are some of the acute effects that we have talked about. But as you can imagine, most people don't engage in this behavior when they're at work or when they're in class or at any other time when a high level of functioning is required. So even if you can think of some individuals in your life that do smoke before going to work or school, most people don't, because they can't do a lot of what they normally do at work or at school when high. Okay, Now, going back to this initial point that most people aren't high when in class or at work, the idea to consider is if marijuana is used only during the evenings and the weekends when one isn't at work or in school, and if these drug-related cognitive deficits don't outlast the period of use, then one can argue that these deficits are harmless because they're just transient, they're temporary. They're not affecting my cognitive functioning the next day when I'm not high and when I'm at school or at work. But then the question is, what if there are residual cognitive deficits from marijuana use? What if you're someone who only smokes during the weekend, but then what if your overall cognitive functioning is still affected as a consequence of your weekend smoking during the weekdays, even when you're not smoking during the weekdays, right? So what if you're not able to perform at your optimal cognitive functioning because of the residual effects of cannabis, of THC? So, or it's possible that heavy recreational use over a long period of time can somehow compromise brain function, so that these cognitive problems then can even persist even after drug use has been stopped, right? So this is an important area to look into for obvious reasons, right? Because now we're considering, could there be these unintended long-term effects? This has been a controversial topic, but some reasonably consistent findings have started to emerge, which I'm going to share with you.